Okay. So good morning, everyone. Moment I started the lecture, it was uh, electricity problem, so it was switched off. So it will take 2 minutes to get the whiteboard started. Okay. So can you see the screen? Last time we have seen what is sampling, what is mixing, what are different types of feedback topology. Can anybody tell me what are the different types of feedback topologies? Yes.
Voltage series feedback, voltage shunt feedback, current series feedback, uh, current shunt feedback.
Very good. Who is this?
Rutuja.
Okay, Rutuja, good. So we have seen that there are four types of feedback topologies: voltage series, current series, voltage shunt, and current shunt. We have seen what is sampling and what is mixing. So where we do sampling and where we do mixing, where we do sampling at the,
Voltage.
we sample either voltage or current, and we sample it from the output part of the amplifier. And where we do mixing, we mix, the mixing is done at the input side of the amplifier. What is mixed? What is mixed? The input signal and the feedback signal. See, input signal Vs and the feedback signal Vs, they are mixed. So depending on this, there what are different types of sampling? Sampling depends on whether you are sampling voltage or current. So depending on that, there are two types of sampling: voltage sampling and current sampling. When you sample voltage, like look here, I'm showing on the cursor. When you sample voltage here or here, this two figure, this one, when you sample voltage, what happens? You have to connect your beta network in shunt with the amplifier's output. So this is the output amplifier available here. RL is the load resistance across which we are getting our amplifier's output. So you see beta network is connected in parallel with. Look at these 2 points. Whenever we have to sample voltage, because voltage is present across this. So if you want some part, you have to connect it in parallel. Similarly, here also, when you want to take some part of output, you have to, as voltage, you have to connect your beta network in parallel with this. Okay. This is voltage sampling. If we want to sample current, you have to connect amplifier's output and beta network in series. So you can form such loop. So, so see, this is the series connection. So this series connection is established here. So current sampling and voltage sampling. While mixing, when you mix the input voltage, okay, so voltage mixing will be done in series. So in this case now, when you have to mix voltage, look at here. So when feedback signal is a voltage signal, then this kind of mixing is right. So here also, when input signal is a voltage signal, then mixing is of series. And when it's a current mixing, So you have to mix two currents. So in this case, it is mixed in, you have to connect the beta networks, output part of beta network in shunt with the current source. So this is your current source. This is the current source and this is feedback network. You have connected both in parallel. So this is how you have to make connection. Okay. Now let us talk about the effect on input and output resistance of an amplifier. So when I talk about a single amplifier, this is my single, this is amplifier, single amplifier A. And when I want to find its input and output resistance, so its input resistance is available at its input terminal, and let's call it as Ri, and output resistance of this amplifier is Ro. Okay. Now, when you connect feedback, it means when you consider the complete network by applying the feedback, we will call the input and output resistance of the amplifier as RIF. That is input resistance, we call it as RIF, and output resistance, we will call it as ROF. So this is your amplifier. It is having its input resistance Ri and output resistance Ro. I'm only talking about this. Okay, let's talk here. So this is Ro is the output resistance of this individual amplifier, and Ri is input resistance of this amplifier without any feedback. Now, when you connect your feedback network, this is also having, let's say, its output input resistance. Now, this is the input part of feedback network, and this is the output part of feedback network. So this feedback network is having its input resistance, okay, and its output resistance, let's say, for example, I will say R beta I and R beta O. Okay. So when you are making connection in parallel, what is happening actually? This resistance Ro and this resistance R beta I, they are coming in parallel, right? When it's a sampling is voltage sampling. So in voltage sampling, you connect this network in parallel. So when you connect this network in parallel, these two resistances, they will get connected in parallel. So what is the net effect on the uh, Ri? What is the net? This must be written as ROF. So what is the effect on the output resistance of amplifier with feedback? Amplifier आहे, याचा फीडबॅक रेजिस्टन्स आहे, लेट्स से सॉरी, याचा आउटपुट रेजिस्टन्स आरओ आहे आणि हा एक नेटवर्क आहे. Okay, some network, and let's say its input resistance is arbitrary. So when you are performing such type of connection, these two resistance will come in parallel. So net resistance ROF will decrease. RO जेवढा आहे याच्यापेक्षा कमी resistance होईल after feedback. Are you getting? So for this case, your ROF will decrease. I'm comparing ROF with this RO, and I'll compare RIF with this RI. तर ॲम्प्लिफायरचं जे ओरिजिनल आउटपुट रेझिस्टन्स होतं त्याच्यापेक्षा जेव्हा तुम्ही सॅम्पलिंग व्होल्टेज केलं तर आउटपुट साईडला तुमचं लक्षात येईल की ROF जो आहे तो कमी झालेला. Okay, now look here. See, here you are, what you are doing? Mixing, series mixing. So input resistance of amplifier, this Ri, and output resistance of feedback network, they will come in series, right? So total resistance will increase. So this Ri is greater, or this RIF is greater now? RIF is greater because you have connected two network in series. Okay. Now, next you will tell me, look at this configuration. This is current series feedback amplifier. Okay, tell me here what will be effect on ROF. This is ROF, and here I want to discuss about RIF. Input resistance with feedback and output resistance with feedback. So, whether this ROF will increase or decrease. Yes, everybody, unmute yourself. What will happen to RF? Increase or decrease? Yes, Rutuja, Harshita.
Ma'am, it will
Increase.
decrease.
Increase. No?
You tell your opinion. This is, let's say, resistance. हा amplifier आहे, याचा output resistance R1 आणि याचे input resistance, let's say, R आहे. I will write here inside RO and RI. जेव्हा तुम्ही बीटा नेटवर्क सिरीज मध्ये कनेक्ट केला इथे तर काय होईल, हा RO आणि बीटा नेटवर्कचा जो काय इनपुट रेझिस्टन्स असेल, लेट्स से आर बीटा आय. ओके, हे तुम्हाला लक्षात राहायसाठी, बिकॉज यू नो सिरीज combination of two resistance yields more resistance. Suppose this is R1 and R2. So when you connect in series, you get output resistance as R1 plus R2. म्हणजे total resistance वाढला. And when you connect two resistance in parallel, so what you get? Suppose one is 100K and another is 1K. तर नेट आउटपुट किती मिळतं तुम्हाला? जो याच्यामध्ये स्मॉलेस्ट असेल त्याच्यापेक्षा थोडं कमी. Okay, so now here you are connecting these two in series, right? So net resistance will increase because of series connection. And here what will happen to RIF? Yes, what will happen to RIF?
It will also increase.
Decrease.
Increase.
Very good, because here input signal and feedback signal we are mixing in series. Okay, so here also RIF will increase. So for current series combination, input resistance with feedback will increase as compared to input resistance without feedback. Similarly, output resistance with feedback will also increase as compared to output resistance without feedback. Clear? Here, come to this. Tell me here, what will happen? Which configuration is this? Where my cursor is present. Which configuration is this?
Voltage shunt feedback.
Very good. It's a voltage shunt. Look at the output side first. How it is connected in parallel, it means voltage is sampled. How it is mixed in shunt, it means it's a shunt mixing. So name is voltage shunt. So what will happen here? What is the effect on output resistance of amplifier with feedback and input resistance of amplifier with feedback? Increase or decrease? Will it increase or decrease? Apply the basic terminology. We will derive the equation later, but you must understand that when we are connecting any two networks in parallel or series, what happens to the effect on resistance? So when you will see any configuration, whether it's a voltage shunt or voltage series, current shunt or current series, so you will immediately come to know what shall I write about the feedback resistance, output resistance with feedback or without feedback. So you simply remember how to write the name of amplifier. I told you, whenever you are writing the name of an amplifier, what shall be the terminology? What I told you, how to remember this? How to remember this? You have this amplifier, okay, input side, output side, okay. What is happening here at the input side? Mixing is happening, is it? And what is happening at the output side? Sampling is happening. Clear? Mixing and sampling. So first of all, you look at the output side, then you look at the input side. When you find here shunt type of connection, when you find here shunt connection, Okay. If it's a shunt connection, it means voltage is sampled. What does it imply? Voltage sampled. Okay. And if it's a series connection, what does it imply? If this is series connection, if you find that beta network which we are about to connect here, if it is having series connection, means what is sampled? Current is sampled. Okay. So look at the output. What is sampled? If voltage is sampled, you write the first word as voltage. Okay. If current is sampled, write the first word as current. Okay. Similarly, either you can sample voltage or you can sample current. Next, you look how it is mixed. So look at the input side of this amplifier. Now this is a feedback amplifier. So further you have a beta network here and you are mixing. So if you find here series type of connection, it makes it right here series. The second word will be series. If you find it is shunt type of connection, write your shunt. So name of the amplifier feedback topology will be written as, whenever you see any name, look at the name. The first word indicate what is sampled. The second word indicate what how it is mixed. So if it the voltage sample and mixed in series, your feedback topology or amplifier will be voltage series amplifier, or it will be current series, voltage shunt or current shunt. So this way you can remember the names of different amplifiers. Got it? Have you understood how to remember this name? Once you remember, now how many names? Now what I will do, uh, I will write the names of amplifier and you will tell me what is the effect on these amplifier, the input and output resistance of this amplifier. So I have, let's say, first. Now tell me the different topologies or different feedback amplifiers name. I will write it. Yes. Please unmute and tell me the names. Come on fast, you know it now.
Voltage series.
Voltage series. Let me write. Okay, next.
Current series.
Current series. Okay. Is this Pajal?
Yes, ma'am.
Okay. Now next member will tell me. What shall I write third?
Voltage shunt.
Voltage shunt.
Voltage shunt. Good. Next member.
Current shunt.
Shunt.
Current
Shunt.
shunt. Very good. Very good. Yeah. So these are my four amplifiers. Now I want to see, this is an important question which will appear in the examination. And if you write proper comparison, you will get full marks. Now what I'm supposed to write here, this is my feedback amplifier. This is the name of my feedback amplifier. Okay, this is my feedback amplifier. Then I will write about input resistance. RIF means input resistance after applying feedback. So what is the effect? And then I will write output resistance, ROF, output resistance after applying feedback. So I want to make comment on this. And I am writing this in comparison with the resistance without feedback. Okay. Fine. So whenever voltage is sampled, whenever voltage is sampled, how is the connection of output of, how is the connection at the output side? Simply, whenever my first letter is 1, sorry, voltage, whenever my first letter is voltage, I will come to know that output connection is shunt. Clear? Is it clear? Everybody?
Yes, ma'am.
Whenever
Yes,
I
ma'am.
am sampling voltage, my output connections, look here, this one and this, output connections are in parallel. So whenever output connection is in parallel, output resistance is about to decrease. So I will write here first ROF. So wherever I find voltage here, I can write that output resistance is about to decrease as compared to resistance without feedback. So here is voltage. Again, I can write the same thing here. Now, whenever my first letter is indicating current, it means how is the beta network and amplifiers output are connected. Look here, for current sampling, how they are connected?
In series.
In
Series.
series. So what is the effect of series connection of resistors? Yes, in this case, what will affect on ROF? Increase or decrease?
Increase.
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 So I will write, very good, very good. So I will write here up arrows, okay, indicating increase. For simplicity, I am showing you so that you will be able to remember. This down arrow indicate decrease. This indicates increase. Again, this indicate decrease. So you understand, right? Increase, decrease arrow. Now come to RIF, second letter. Series, series, shunt, shunt. So you will immediately understand now. If second letter is series, it means at input side, mixing is happening in series. So what will be net effect on RIF?
Increase.
Very good. It will increase. So again, here in the current series, I will come to know that when it's a series mixing, input resistance is about to increase. Now, shunt, what is the effect?
Decrease.
Decrease.
Decrease. So whenever second letter, remember how the trick to remember this. You must understand the concept. Similarly, you can remember, write the name of the amplifier, feedback amplifier. Look at the first letter. First letter belongs to type of sampling. So think about the output terminals and feedback network, how they are connected at outside. So for voltage, they are connected in shunt, which implies decrease in the resistance. For current, they are connected in series, which implies increase in the current. Got it? Similarly, look at the second letter. The second letter indicates the type of, the way of mixing at the input side. So when it is series mixing, so definitely it is going to increase the resistance of amplifier with feedback. So wherever you find series, you can write increase. Wherever you find shunt, you can write decrease. This is how to remember this. Okay. Is it clear? Effect on input and output resistance for different types of feedback topology or for different types of feedback amplifier. Okay, so when you want higher inputs, so you can prefer this configuration, voltage series and current series, right? So feedback amplifier you can select depending on the requirement of your currents. Fine. Now moving on. So is it clear to you? And one more advantage I told you when I taught you the bandwidth of an amplifier, I told you that gain and bandwidth product is always constant. One thing I told you that gain and bandwidth product is always constant. Now, when gain and bandwidth product is constant and the gain of negative feedback amplifier is decreasing, the gain of negative feedback amplifier is less. Okay, so what will be the effect on bandwidth? What will be the effect on bandwidth? गेन आणि बँडविड्थ प्रोडक्ट ही नेहमी कॉन्स्टंट राहते. गेन इनटू बँडविड्थ is always constant. Now for a negative feedback amplifier, you know, gain is less, gain reduces. So what will happen to bandwidth? It will increase. Okay, so in all four cases, if you see bandwidth, if you compare this bandwidth without feedback, so you will find everywhere that bandwidth is increased. And what is bandwidth? Can anybody define what is bandwidth? You know that? Yes, what is bandwidth? You can define bandwidth.
Range between two frequencies that can be amplified by amplifier.
Yeah, range, you should say a range of frequency that can be amplified, and this range is calculated as higher cutoff frequency minus lower cutoff frequency, fh minus fl. Good. Now, so this is how the effect on input and output resistance of a feedback amplifier. Now, in terms of input increases and decreases, I told you. Now we have to write that figures or formula which proves whatever I told you. Okay, I told you conceptually. I told you conceptually so that you will remember it. Now we don't have the derivation this time. Otherwise, the derivations were also included in the syllabus. But now we have to actually see why I am saying whenever there's a series or parallel connection, one can easily understand. But then I must have some figures by with which it increases or decreases. So let's talk about that. Okay. Let's see one more advantage. Yeah, when I told you the advantages of feedback amplifier, I said gain stabilization. Yeah, I said gain stabilization takes place in negative feedback amplifier. Okay. Now, what is this gain stabilization? And I told you that time that we will derive an expression for that. Okay. So let's derive the expression for this, and then we will come back on this because you need to understand here what is D. Okay. So at the end, I will be telling you about this desensitivity factor, sensitivity, desensitivity, and then we will write this term in. We will understand what is this D and S, what you can see on the PPT. Like this. Okay. Let me clarify you here. When we say gain, we say that gain decreases in negative feedback amplifier. Now, what are our gain definitions we have seen in the types of amplifier? Okay, gain we said when it's a voltage amplifier, we call it as gain AV without feedback and AVF with feedback. When it's a transconductance, now see when it's a when the feedback topology is voltage series, okay, So at both side you find their voltage. When it's a voltage series, so input there is a voltage and output is also voltage, because see, we have connected shunt. There is a shunt connection, means we are sampling voltage. So at input side, input source is voltage and output source is output is also voltage. So which type of amplifier this is? Voltage amplifier. Here in this circuit you see input is voltage and output is current. In this circuit, input is current and output is voltage. In this circuit, input is current and output is also current. Okay. Whenever there is mixing in series, it means it's a, sorry, whenever there is sampling, circuit looks like a series connection, it means we are sampling current. Okay. So input is voltage, output is current here. Input is current, output is, sorry, input is current, output is also current. So which amplifier is this?
Current shunt.
Input amplifier. In first of all, we learned 4 amplifiers, na? Voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. Do you remember? Then these are the feedback topology. Now, when I say voltage series amplifier, means which amplifier is this? It is nothing but it's a voltage amplifier. A voltage series topology hai. This is current series, this is current shunt, and this is voltage shunt. Okay. Now, what is the amplifier? The basic type of amplifier is voltage amplifier, current amplifier, transconductance, and transresistance amplifier. So if you see voltage series amplifier, you know, input is voltage, output is also voltage. So I will define its gain as AV equal to output voltage upon input voltage. This is the voltage amplifier. Look at the current series. What is your input signal? Vs means V. And what you are sampling? Current. It means output is I. So which amplifier is this? Current. Its gain will be the ratio of I by V. So which amplifier is this?
Transconductance amplifier.
Transconductance. Good. So transconductance amplifier. Look at this amplifier. Current shunt. Input is current. Output is also current. Which amplifier is this?
Current amplifier.
Current amplifier.
Current amplifier. So I will write its gain as AI, which is equal to output current upon input current I. Look at this amplifier. What is input? I. What is output? Shunt connection, I means voltage. So I will write its gain as ratio of V to I, means which amplifier is this?
Transresistance amplifier.
Transresistance.
Good. Very good. Okay, so feedback topology you can relate with the basic amplifiers that we have learned. So voltage series amplifier is nothing but your where is my sharing window gone? So voltage series means it's a voltage amplifier. So I will write its voltage gain as AV and AV. Current series means it's a transconductance amplifier. Voltage shunt means transresistance amplifier. Current shunt means current amplifier. So when you think of the gain in negative amplifier, gain reduces. Okay. Now by what factor this gain reduces? So when you apply negative feedback, your original gain gets divided by a factor D, which is called as desensitivity. Okay. What is that? I will tell you. Now here also GM gets divided by G. So GMF is equal to GM by D. RMF means the trans resistance gain, that is the gain with feedback, is equal to Rm upon D, where Rm is the gain without feedback. So without feedback gain is higher, and with feedback it gets divided by factor of D. Now we have commented for everything how the input resistance is about to increase, where it will decrease. Okay, so here when it increases, remember the input resistance of amplifier get multiplied by factor D, and whenever we say decrease, it's get divided by D. Okay, so wherever we have written in our whiteboard, wherever we have written increases, so here input resistance Ri will get multiplied by D. Wherever increases, it will get multiplied by D, and wherever decreases, it will get divided by factor of D. Here also, wherever we say output resistance is increasing, it will get divided by, it will get multiplied by D, and wherever we say output is decreasing, it will get divided by D. Okay. D is called as desensitivity. Okay. Now, what is this desensitivity? This desensitivity D is given by 1 plus A beta. 1 plus A beta. Okay. Remember this 1 plus A beta. We will go further in more detail what is this desensitivity actually. Is it clear? Understood? Yes or no? How the input resistance and output resistance with feedback increases or decreases, or how the negative feedback impacts on the input and output resistance of feedback, different negative feedbacks. Is it clear?
Yes, ma'am.
Yes,
Okay,
ma'am.
now we will, good. Now we will derive the equation for desensitivity. Okay, let's say, sorry, we will derive the equation for stabilization of gain. Gain stabilization म्हणजे काय? So we have seen when you apply negative feedback, so we write this as gain with feedback. And what is its formula? It is A upon 1 plus A beta. Okay, we had derived this already. Now, when I want to find changes in the gain, variation in the gain, I have to differentiate this gain. That derivative means it gives us some rate of change. It gives us changes. It tells us about change. So let's take the derivative to find. I have to prove that when we apply negative feedback, the gain variations are reduced. The gain is stabilized. It's not fluctuating. It's not varying. Okay, so that we have to prove. So let's differentiate both sides with respect to A. So what this will be, if I want to differentiate with respect to A, this will be DAF upon DA. Changes in gain with feedback with respect to changes in gain without feedback. Okay, now if you find derivative of this, let's call this as equation 1. If you find derivative of this, you know you can apply the UV rule. So it will be 1 plus A beta, this denominator, into derivative of this will be 1 minus, take the derivative of this into this as this is u, derivative of finding u by v rule, you know. So this will be, what is derivative of 1 plus A beta with respect to this? It will be A. It will be beta. If you differentiate 1 plus A beta with respect to A, it will be beta, and A will remain as it is. So combinedly divided by one plus square. So if you solve this, it will be 1 plus a beta minus a beta divided by 1 plus a beta bracket square. So this will get cancelled. It will be 1 upon 1 plus a beta square. Okay. What is this? DAF by DA. Now if I want to find, this is what DAF, changes or variation in the gain with feedback with respect to changes in the gain without feedback. Now if I want to find only changes in the gain with feedback is equal to, so 1 upon 1 plus a beta square into this dA will go here, dA. What does it mean? Changes in the gain with feedback. Compare this now, compare this changes in the gain with feedback. How much it is? It is changes in the gain without feedback divided by 1 plus a beta square. म्हणजेच काय होत आहे की हा जो changes in the gain, if you don't apply feedback, you get dA. If you don't apply feedback, let's say the variation in the gain is dA, but when you apply feedback, so what is your dA? Your dA gets divided by 1 plus a beta. Your numerator is greater, so it means your changes in the gain with feedback has reduced as compared to changes in the gain without feedback. It means your gain is stabilized. What does it mean? The gain is stabilized. This indicate less variation means gain stabilization. Because changes in the gain without feedback are further divided by 1 plus a beta factor. And this is equal to your DAF. This is called as stabilization of gain. Now, further, what we'll do, we will divide this term. Idea. We will divide this DAF by AF because we want fractional changes DAF upon AF. Changes in the gain with feedback. So I can get this as 1 upon 1 plus a beta bracket square into dA. I have to divide this term as well. Okay. What is my dA? AF. I will rewrite this as 1 plus 1 upon 1 plus A beta square into what is my DF? What is my AF? This is AF in given in equation 1. A upon 1 plus A beta. So I'll write this as, this is 1 by AF, no? So this will become reverse of this ratio. 1 plus A beta upon A. This is 1 upon AF. हा जो AF आहे ना, हा 1 by AF आहे. So I have written the value of 1 by AF as reversing this ratio into dA. What I got? Now this will be cancelled. So I get 1 upon 1 plus A beta into dA just a minute. I have this is 1 plus A beta upon A. Okay, so this will become 1 plus A beta upon A. So what I got? dA by A. Which clearly tell you that fractional changes in the gain with feedback is equal to fractional changes in the gain without feedback multiplied by 1 upon 1 plus A beta. Right? So gain is stabilized. Now from this equation, the term from this equation, this term 1 upon 1 plus A beta is called as sensitivity or transfer gain. 1 upon 1 plus A beta is called as sensitivity, or it is also called as transfer gain. And this factor, the reciprocal of sensitivity, is called as desensitivity. Reciprocal of sensitivity is called as desensitivity. So what is reciprocal of sensitivity? Sensitivity is equal to 1 upon 1 plus A beta, and desensitivity is equal to 1 by S, that will be equal to 1 plus A beta. So when your gain increases or decreases, I have shown you how it gets divided or multiplied by factor of D. So this factor of D is nothing but this one, 1 plus A beta. What is D equal to? D is desensitivity and it is equal to 1 plus A beta. Understood? Is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Good. Let's take attendance now. Oh, it's over. Somebody please remind me when we start lecture. Please remind me to start the attendance. Otherwise, our lecture gets over and then I cannot start that attendance. Please give your attendance. Nilesh Aga,
Present, ma'am.
Aditya,
Present.
give attendance fast. Pejal,
Present,
Parth
ma'am.
Baviskar,
Present, ma'am.
Vaibhav,
Present, ma'am.
वैभवी भोसले,
Present, ma'am.
दय बोरसे, हर्षदा चौधरी,
Present,
Present,
ma'am.
ma'am.
सिमरप्रीत चावला,
Present, ma'am.
ऋतुराज चोलके,
Present, ma'am.
कल्पेश देशमुख,
Present, ma'am.
कल्पेश देशमुख,
Present, ma'am.
हर्षदा सावंत देशपांडे,
Present, ma'am.
हर्षद हर्षद देशपांडे, हर्ष धनावडे,
Present, ma'am.
धनावडे, श्रुतिका ढोरे,
Present, ma'am.
विवेक गारगोटे,
Present, ma'am.
अर्पिता गोजागे,
Present, ma'am.
साहिल हिवराळे,
Present, ma'am.
रुपेश जाधव,
Present, ma'am.
समृद्धी काकडे,
Present, ma'am.
अभिषेक कानडे,
Present, ma'am.
Abhishek, you please take your attendance. Okay, it is little bit reduced. So keep many time you used to quit from the meeting, and at the time of attendance, I don't find you. So if you are, if such case happen, you please convey to that teacher.
Yes, ma'am.
Sakshi Karke,
Present, ma'am.
Tanmay Khairnar,
Present, ma'am.
Abhishek Lavate,
Present, ma'am.
Yash Lavate.
Present, ma'am.
Yes, your attendance need to be improved. Shruti Mandale,
Present, ma'am.
Yalal Mulla,
Present, ma'am.
Rishikesh Mungse,
Present, ma'am.
Sahil Naikade,
Present, ma'am. Present, ma'am.
Varun Naikade,
Present, ma'am. Present, ma'am.
Piyush Naimade,
Present, ma'am. Present, ma'am.
Chetan Patel, Chetan Patel, Prathamesh Patel,
Present, ma'am. Present, ma'am.
Samruddhi Patel, Samruddhi Patel, Aditya Pawar,
Present, ma'am.
Omkar Parande,
Present, ma'am.
Sanjay Prasad.
Present, ma'am.
Aditya Pawar is there.
Yes, ma'am. Present.
Prathamesh Landge,
Present, ma'am.
Ritika Bankar,
Present, ma'am.
Parth Sawant, Parth Sawant, Piyush Savkar,
Present, ma'am.
Suyash, Anusha Shevle,
Present, ma'am.
Shubham Shisat, Ankit Singh, Tejas Sonavne,
Present, ma'am.
Solonu Sonkamre,
Present, ma'am.
Akshay Sutar,
Present, ma'am.
Abhishek Singale,
Present, ma'am.
Yajnesh Warpe,
Present, ma'am.
वैभव वाखरे,
Hello, ma'am.
वैभव वाखरे,
Ma'am, 31 is present.
Ma'am, roll number
who is
11
this?
present.
Chetan
Roll
Patil,
number
ma'am.
11 present.
Network.
Okay, then Chetan Patil present.
Yes, ma'am.
Parth Sawant is there. Suyash, Shubham Shisat, Ankit Singh, Vaibhav Vakre. Okay, you can leave the meeting. I will save. If you have any problem of mic, write in chat box.